Welcome back. We spent some time talking about the resolvent operator and the Cayley operator of a relation. And now we're going to use those for another important instance of operator splitting. We've already seen examples of operator splitting, the most prominent being the proximal gradient mapping, which is a composition between the resolvent operator for the function that's proximable composed with the gradient operator for the function that's smooth. Now we're going to use the Cayley operator to see this as well. Remember that the goal of operator splitting is to solve a problem that involves, if it's an optimization problem, solve a composite optimization function in a way that's decoupled. So we want to solve a composite problem with an iterative procedure that involves operators that deal with each term in the composite objective separately. Or they're split. It's like a divide and conquer approach. And again, the main example that we've seen here is the proximal gradient algorithm to minimize the composite function f of x is equal to g of x plus h of x, where g of x is smooth and h of x has an easy to evaluate prox operator. And of course everything is convex. In particular for us, the context that we're going to focus on is the setting where we want to solve a set of generalized equations in the language that we've developed when we were talking about relations. So f is a relation, and in particular we're going to assume that f is some maximal monotone relation. And we want to solve the generalized equation 0 is an element of f of x. And now the composite structure that f has is to say that f is equal to a plus b, where we're also going to assume that a and b are maximally monotone. Now recall the connection to our canonical example in all of this. An operator is monotone if the subdifferential of a convex function is monotone, and if that function is closed, then the subdifferential is a maximally monotone operator. So this is a very typical setting for us. This amounts to a special case, if a and b are subdifferentials, of trying to solve the optimization problem, minimize f of x plus g of x, or g of x plus h of x, whatever it is that we call it. We're going to stay in the slightly more general setting of maximal monotone relations and maximal monotone operators, and then specialize it to the optimization setting in a minute here. Okay, so our proposition, the main proposition, is that we can use the Cayley operator in order to solve this set of generalized equations. 0 is an element of f of x in the setting where f is equal to a plus b, and get to enjoy operator splitting. So our proposition is as follows. 0 is an element of ax plus bx. In other words, x is a solution to this set of generalized equations. is equivalent to writing that Z is a fixed point of the composition of the Cayley operators that correspond to relations A and B, or operators A and B. Remember, there's a bit of abusive notation there. CA composed with CB of Z equals Z, and X is equal to the resolvent operator with respect to operator B of Z. So let's quickly just recall the definitions here. Recall that for a relation A, or let me use, so the resolvent operator of a relation A, and similarly for a relation B, and some non-negative constant, is defined as R, I'll use R subscript A. This is equal to identity plus lambda times A inverse. And recall that for the setting where A corresponds to the subdifferential of a convex function, then the resolvent operator on its own corresponds to the proximal point algorithm with respect to that function. And the Cayley operator is defined as 2 times R minus the identity. And then similarly for RB and CB. So let's move to the proof of this this proposition. The first step is to observe that this is equivalent to, or sorry, in particular, this condition here is equivalent to the following: CA CB of Z equals Z, X is equal to RB of Z, is equivalent to 4 equality conditions. There's no magic here, just rewriting. It's simple to observe, but it will just be a little bit easier. It's equivalent to X equals RB of Z, Z tilde equals 2X minus Z, X tilde is equal to RA of Z tilde, and Z is equal to 2X tilde minus Z tilde. Just plugging in, you'll immediately see that these two are equivalent, and again, using the definition of C with respect to R. C is equal to 2R minus the identity. So it's straightforward to check this. So now note that this implies, in particular, if I subtract, let me label these equations, 1, 2, 3, 4. If I subtract 2 minus 3, I get that Z tilde minus Z is equal to 2X minus Z minus 2X tilde minus Z tilde, which is equal to twice X minus X tilde plus Z tilde minus Z. And from this, we conclude that if 2 and 4, that if 2 and 4 hold, then X is equal to X tilde. Okay, so what we're doing now is again deriving consequences of Z being a fixed point of the composition of CA and CB, and X equaling the resolvent with respect to B of that fixed point Z. So if that's true, then 1, 2, 3, 4 hold. And if 1, 2, 3, 4 hold, then in particular that implies that X is equal to X tilde. And if we plug that into the fourth equation, then the fourth equation now reads that 2X is equal to Z tilde plus Z. Okay, let's keep going. The first equation tells me that X is equal to the resolvent of Z. Writing out the definition of the resolvent, this is just equivalent to X is equal to I plus lambda B inverse Z, which is the same as writing that Z is an element of X plus lambda B of X. And similarly, we have that X is equal to X tilde. We concluded this above. And X tilde, by definition, this is by equation 3, is equal to RA of Z tilde. And so by the same exact chain of reasoning, we arrive at Z tilde is an element of X plus lambda A of X. I would have had an X tilde there, but we concluded already that X tilde is equal to X. So let's now add these. How shall I label these? Let's call these, I guess, I and II. So adding these, I plus II, what does this tell us? It tells us that Z plus Z tilde, which is also known as 2X, this is equal to Z plus Z tilde, is an element of X plus X, 2X, plus lambda A of X plus B of X. And you can see that this is exactly, therefore, what we wish to conclude, because this is the same by canceling 2x as writing that 0 and recalling that lambda is positive. I might have written lambda as non-negative. Let's see, where's lambda? We're taking lambda to be strictly positive here. Yeah, recall lambda is strictly positive. This is the same as writing that 0 is an element of ax plus b of x. So again, if z is a fixed point of the composition of CA and CB, and if x is equal to RB of z, this implies that x solves this generalized equation. 0 is an element of ax plus bx. The converse also holds, but for us in particular, this is what we need, because it's giving us an algorithm for solving this. And also you can see that this exactly fits our divide and conquer approach, because we are using CA and CB and RB. We're only using operators one at a time that depend either on A or on B. So this gives us immediately a candidate algorithm for solving such a problem. So to solve 0 element of A of x plus B of x, option 1 is to write the algorithm zt plus 1 is equal to CA composed with CB of zt. And then finally, once we find a fixed point, set x equal to RB of that fixed point. But the core of it, the core of the iteration, is iterating applying CA and CB. Now, in the context of what we've discussed when talking about fixed points and non-expansive operators, we showed in the previous lecture that CA and CB are non-expansive, and this implies that the composition is non-expansive. Now, if either CA or CB is a contraction, then the composition is now going to be guaranteed to be a contraction, and in that case, we know that ZT is going to converge to a fixed point at a linear rate. But if we don't know that, then we don't yet have enough to determine that this iteration is going to converge. So we need a little bit more. Just in terms of the history and the literature, this iteration is called the Peaceman-Rachford algorithm. So just this iteration here is called Peaceman-Rachford. And now we've also discussed whenever we have a non-expansive operator, in order to guarantee that we have convergence, all we need to do is form an averaged operator, since if we average a non-expansive operator with the identity, it's going to have the fixed points, and as we've discussed in previous lectures, we have now a guarantee of convergence. And this is, in fact, the Douglas-Rachford algorithm. Sometimes called Douglas-Rachford splitting. It's really just damped Peaceman-Rachford algorithm. So we use ZT plus 1 is 1/2 the identity plus 1/2 CA CB composed with ZT. I'm sorry, CA composed with CB evaluated at ZT. So in particular, since CA and CB are non-expansive, the composition is non-expansive, this isn't, not only is it alpha averaged, it's 1/2 averaged, which is also known as firmly non-expansive. Note that we are guaranteed to have convergence as long as we choose any averaging that's non-trivial. So we don't have to choose 1/2. 1/2 gives us the classical Douglas-Rachford splitting algorithm, but we don't need to use this. So what does this finally guarantee us? It guarantees us that from our work on alpha averaged operators, in other words, on the work that we've done in these lectures for alpha averaged operators, we know that iterating this is guaranteed to converge to a fixed point as long as the fixed point of our operator is not empty. So if 0 is an AX plus B of X, if this generalized equation has a solution, then the set of fixed points of CA composed with CB is non-empty, and we know therefore that ZT is going to converge to this set of fixed points. And as we mentioned, the averaged operator is going to have the same fixed points, which is why we have this conclusion. Okay, so now let's go back and apply it to our canonical setting of interest. So let's apply it to minimizing this composite function f of x plus g of x, where we'll assume that f and g are both closed convex functions, and therefore that guarantees us that their subdifferentials are each maximally monotone operators. And let's see what Douglas-Rachford tells us. So again, the DR algorithm, as we just wrote it, is the main iteration. ZT plus 1 is equal to 1/2 of the identity plus CA composed with CB of ZT, and then finally setting X equal to RB of Z. Now remember the basic definitions. So the resolvent of an operator is, just like we wrote down a few slides ago, identity plus lambda A inverse, and CA is equal to 2 of RA minus identity. And also recall what the resolvent is. The resolvent is our proximal. For this special case where A, so let's write this clearly. So for us, A is equal to the subdifferential of F, and B is equal to the subdifferential of G. And therefore in this case, RA of Z is equal to the prox of the prox operator with respect to F of Z, and similarly RB of Z would be the prox operator with respect to G of Z. So let's work backwards and write down what the traditional one way is that you might see Douglas-Rachford algorithm written down. So for the problem of minimizing f of x plus g of x. So this is a common. There's many ways that it's written down, and in fact, we're also going to look at different ways where we can rewrite it. But one way that it's written is iteration of xk plus 1 is equal to prox with respect to f of yk, and yk plus 1 is equal to yk plus prox with respect to g of 2 xk plus 1 minus yk minus xk plus 1. Now when you're looking at this, first of all, maybe it's not intuitive where it came from. In part, that's the goal of giving this development, but still we should already be seeing some things that are going to look familiar, that shouldn't surprise us too much. So for example, we know that the Cayley operator is 2r minus I, so we should be seeing those kinds of things pop up here. Okay, so let's write this down and see and plug in things, and then really identify that this expression here is exactly the same as basically this this iteration that we have up at the top of the slide. So we've got xk plus 1 is equal to I minus yk. That's what this first line says, and this is, I'm putting it in the language, in our general language of resolvent and Cayley operator. This is exactly Rf of yk, and yk plus 1, plugging this in, is exactly equal to yk plus prox. Remember, is the resolvent with respect to g, so instead of writing prox g, I'll write rg. And where is it evaluated? At twice xk plus 1. Xk plus 1 is Rf, so I've got twice Rf. And rather than writing yk, let me factor that out and write it in this way. So we can identify immediately what's sitting here as the Cayley operator of f, minus xk plus 1, which again is Rf of yk. So this is equal to yk plus rg composed with the Cayley operator of f of yk minus rf of yk. And now I'll write this as rg cf of yk. That's the second term. And now this is just simple algebra here. Minus 1/2, so that I can make another resolvent appear, another Cayley operator appear. 2rf of yk minus yk. So we're good with rf. I have that's minus 1 copy, but now I have a plus half yk, whereas in the line before I had an entire yk, so I need to add back 1/2 yk. And so you can see that this is now rg cf of yk minus 1/2. And what do I have inside here? I have 2r minus the identity, so that's 1/2 times the Cayley operator, evaluated at yk, plus 1/2 yk. This is now equal to, let's bring the 1/2 yk to the front. I've got 1/2 yk plus 1/2 of 2 rg times cf of yk. That was this term right here that I just pointed to, minus this term, and since I already factored out the 1/2, this is just going to be cf of yk. And you can see what I have here. I have 2 rg minus the identity evaluated at cf of yk, which is exactly cg composed with cf. So this is equal to 1/2 times the identity plus cg composed with cf evaluated at yk. So this is precisely what we have. The Douglas-Rachford algorithm is exactly equivalent to this form. It's really nothing more than the iteration, the composition of the Cayley operators of that correspond to the subdifferential of f and the subdifferential of g in a damped or averaged iteration. Let's give a few equivalent formulations of the DR algorithm. What I had written on the previous page is xk plus 1 is equal to the prox f of yk, and yk plus 1 is equal to yk plus prox g of 2xk plus 1 minus yk minus xk plus 1. We can rewrite this as just flip the order of these iterations. Yk plus 1 is equal to yk plus prox g of 2xk minus yk minus xk, and xk plus 1 is equal to prox f of yk plus 1. Now, introducing a new variable uk plus 1 is updated as prox with respect to g of 2xk minus yk. And now I can simplify my update for xk plus 1 as prox f of yk plus uk plus 1 minus xk, and yk plus 1 is equal to yk plus uk plus 1 minus xk. And now changing variables to using wk is equal to xk minus yk, we get uk plus 1 is equal to prox g of xk plus wk. Xk plus 1 is equal to prox f of uk plus 1 minus wk, and wk plus 1 is equal to wk plus xk plus 1 minus uk plus 1. This should make us remember, this should make us think a little bit more, it should be reminiscent of the types of algorithms that we've been seeing, where we have a simple step with respect to g, a step with respect to an operator of f, and then something that somehow combines them in a simple way. We've seen this with algorithms in the dual in particular. Note that we're not yet doing anything in the dual right here, so we don't need the dual for anything so far. The splitting is accomplished as is by the property of the composition of CA and CB. But I'm explaining, why, though of course these are all equivalent, this makes it even more clear that I have my update consists of evaluation of a prox operator with respect to G, a prox operator with respect to F, and then combining these results in this additive way. One final point is that we can also consider scaling, and it turns out that the Douglas-Rachford algorithm is not invariant to scaling. So what I mean is, for any lambda that's positive, rather than solve minimize f of x plus g of x, of course this is equivalent to minimizing a scalar multiple of this. Now in this case we can apply dr to these new scale functions, and in fact we're going to get something different. So the original formulation of dr would look like xk plus 1 is equal to prox of lambda times f of yk, and yk plus 1 is yk plus prox of the scaled function lambda g evaluated at 2 xk plus 1 minus yk minus xk plus 1. And in the equivalent formulation that I wrote on the previous slide, this would correspond to uk plus 1 is equal to prox lambda g of xk plus wk, xk plus 1 is equal to prox lambda f evaluated at uk plus 1 minus wk, and wk plus 1 is equal to wk plus x k plus 1 minus uk plus 1. We should think through what are the implications of choosing a different lambda. As long as lambda is non-negative, we're going to have convergence. We're going to have convergence, but the algorithm itself is not invariant. And remember, the trade-offs of choosing different lambda is that the prox operator is going to be doing something different. So again, this is not invariant with respect to scaling. Where we're going next is we're going to see some examples of Douglas-Rachford, and then we're going to look at what Douglas-Rachford looks like in the dual. We'll pick this up next time.